reciprocal function. So let's see how many functions we know thus far. You actually only know officially of two functions. You know this function. What do we call this one? The linear function. And what do we call this function? A quadratic function. And that's all you know. So we can't do function aerobics if those are the only two functions that you have in your arsenal, right? So let's bring in two more functions. And the first function that we're going to look at is called the radical function. Now, radical, we know what that is, right? That's a radical symbol. What do we call whatever goes under the radical symbol? The radicand. And just as a review, what is this little number called? Index. And what is this little number called? Power. Yeah, good. Okay, so this is a radical symbol. And a radical function, okay, what is the opposite of taking the square root? What does a function x squared look like? Okay, what is the opposite of that? Is that because you saw it on a piece of paper, Leo? Yeah, but like we've got this. This is not the opposite because I know that this is just a negative a value. But the opposite of a quadratic function is a radical function. Can anyone see the mistake I'm making right now? This is, yeah. Oh, yes, I thought you were going to, yes, of course you can. Okay, think about it. This is a quadratic function, and I'm saying, look at me. This is a radical function. No, it's not, Miss Sly. Why is it not? Do you need a ruler? Okay. Okay. What is my mistake? Yes.
The function.
Beautiful. Why is this a mistake? So Timo's saying the mistake is you can't call it a function. Why not?
Because it doesn't pass VLT.
Beautiful. Correct? This is not a function. It fails the VLT. But I still want a radical function. I want it now. Well, you'll have it. Okay. So if a radical function is written as f of x equals the square root of x, let's put some inputs in. So when the input is 0, what's the square root of 0? 0. When the input is 1, what's the square root of 1? When the input is 4, what's the square root of 4? 2. 9, square root of 9, 3, square root of 16, 4. Notice that the inputs I've used have perfect squares, right? I'm not going to write 3 as an input because the square root of 3 is like 1.7 something, 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 right? And I can't graph that perfectly. So when I'm graphing the radical function, I choose my inputs carefully. I only choose inputs that are perfect squares. And so when I graph this, do you have it graphed in your booklet? Okay, look what happens. Okay, let's connect the dots. Where would the next x value be? Oh, wait, take that back. 36, yeah, and we would get, okay. Beautiful. So does this function exist at a non-perfect square like x is 20? Yes, it does. And I know the value is somewhere between 4 and 5. Okay, so it's a continuous function, but when I want to draw it, I use inputs that are easy to use. Okay? And so why did the table of values not include negative x values? Well, what would we say? Yeah.
It would be imaginary or
Okay, So let's see what would happen. If I had negative 25, what would my answer be? What's the square root of negative 25? Yeah. Yeah, or 5i, right? And Mustafa's right. They would not be real values. So let's write an example. If we have negative 25, well, that would give us 5i. So negative x values give imaginary numbers. Imaginary values. And we cannot graph imaginary values, right? On this graph. If you have an imaginary axis, you can graph it, but we're not using imaginary axes. Yeah.
Is that why it's still technically a function?
Yes.
Because of the
Because we're only, yeah. If we don't use negative x's, we end up with just no, sorry, take that back. The negative x's would have been here, right? If I'm saying negative 25 is my x, well, that's here. Okay. All right, connect the points and create a smooth continuous curve, including arrows where appropriate. So here's the question. For this function, how many arrows do I use? Just one. Okay, there's only an arrow here to indicate that the function keeps going on forever and ever and ever. And you need to use arrows on your functions to show that they continue. The function does not continue into the negative x-axis. As such, there is no arrow at the 0. Okay, the function starts at x equals 0. And we call this a parent function. Okay, the parent function is like the basic function. After that, we start moving it and transforming it. Yes. Yes. All right. Let's state the domain and range of the parent function of a radical function. So let's start with domain. Because it's continuous, we have to use the notation that x belongs to a set of real numbers. So all of the real numbers with one restriction, such that, right? And then this part of the domain is called the restriction. Well, what's the restriction? X not just greater than 0. Beautiful. Okay? So x is greater than and equal to 0. Instead of saying my bad, why don't you say thank you, Marley?
Thank you, Marley.
That was beautiful.
No problem, Liam.
Beautiful. All right. So what we're saying is this function exists everywhere along the x-axis as long as it is greater and equal to 0. Okay, how about the range? So you go ahead and write the range because it's very similar to the domain. Yeah. I think someone's asking, right, to go to the bathroom? Has everyone gone? All right, go ahead. Okay. So what I want to do right now is fast forward to our summary of parent functions. Okay, we're going to do one parent function at a time. So a parent function is the basic function where there are no basic function with no transformations. What's a transformation? A vertical stretch is a transformation. A horizontal translation, a reflection in the x-axis, those are all transformations. So if you notice this equation, there are no other numbers. It's just x squared or x or square root of x. So this first function we call the linear function. And the most basic or the parent function of a linear function is one where the slope is 1 and the x-intercept is 0. So the x-intercept is 0. And if the slope is 1, let's just remind us what to do there. If slope is 1, that means it's 1 over 1. That means we go up 1, across 1. So if my x-intercept is here, I go up 1, across 1 to get the next dot. Up 1, across 1, up 1, across 1. So when we are drawing this function, it's basically at a 45-degree angle. And there are two arrows. And when we draw a function, we must label it, meaning we write its name next to it. So we write f of x equals x. So you didn't even realize it in grade 9, but you were doing transformations already because you were doing stretches by changing the slope, and you were doing vertical translations by changing the y-intercept. So if we go into this table, for the linear function, the domain is that x belongs to all of real numbers, because the linear function goes forever and ever and ever along the x-axis, right? It never stops. There are no restrictions. How about for the range? Any restrictions? No, it goes up and up and up forever and ever. So the range of a linear function is that y belongs to the entire set of real numbers. 1, 2, 10, a million, infinity. Hi, Sebastian. We don't yet know what an asymptote is, but I'm going to tell you the linear function does not have an asymptote. Not applicable, NA. And so the last point of key points, that is the key dots on the graph that'll help us remember how to draw this function. So I might say -1, -1, 0, 0, 1, 1. Right? For the linear function, if I have 3 points, I remember these. And the point of making this chart is so that you can remember, you need to memorize how to graph all the parent functions. Let's do the second one that we know well, and that is the quadratic function. Okay, do you remember how to graph the parent function with absolutely no transformations? Where is the vertex? And what do we call that point? The origin. Yes. And then we use the step pattern of 1, 3, 5, right? So 1 across, 1 up, 1 across, 3 up. And because it's symmetrical, right, we can just copy the dots on both sides. Smooth curve to connect, and an arrow on each end to show that the quadratic functions continues to open and open and open. If you think about horizontally, will it ever stop opening up horizontally? No. So that means that the domain of a quadratic function is the entire set of real numbers with no restriction. But for the parent function of the parabola, there is a restriction in the range. So y belongs to all of the real numbers with the restriction of what? Where does y not belong? Yeah, so what do we write? Y is greater than and equal to 0. Nice. Asymptotes, again, not applicable. Key points. I might say this. Vertex is at 0, 0. And then how do I remember to draw it? Well, I just use the step pattern. 1, 3, 5. Right? That's my helpful hint about how to draw the parent function. So those are the ones we've known. Now let's add our new function, the radical function. Okay, so we remember that it's a parabola flipped by 90 degrees. Where does it start? At the origin. And I'm going to tell you something. You know how a parabola follows a step pattern? Well, a radical function also follows a step pattern, but it's the opposite. Instead of going one across and then changing how much you go up, you go one up and change how many points you go across. So we go one up, one across, one up, 3 across, one up, 5 across. So we're using the step pattern, but sideways. And so if I think of this as the parent function, the domain does have a restriction, right? X belongs to R such that, what's the restriction? Yeah, greater than and equal to 0. And the exact same restriction for the range, right? Again, no asymptotes yet. And then for key points. Yeah.
Sorry, why is it y equal is it has to be greater than or equal to 0 if it goes into the negative?
For
we only did
this,
one.
that's right. That's right? Because this part would make it not a function, right? Then it's like, oh, I failed the vertical line test. So the radical function is the parabola flipped, but only half of it. And we'll get more into why that is. One of the reasons is because then it's not a function. Okay, so key points, 2 options. One option is that you list the points. And remember, for the x value, I always take the one that has a perfect square. Okay, or we say 0, 0 is our starting point. We don't call it a vertex, right? Because the vertex is where the graph starts changing. And then we use sideways. Okay. I wasn't sure what word works, but if you need to, I'll write one up, one across, one up, 3 across, one up, 5 across. So you write what works for you, right? If you have yet a different way to remember how to graph the parent function, then you write it that way. Okay. Okay. Finally, let me introduce this idea of the asymptote. What is it, Miss Sly? I'm so intrigued. Okay, well, let's take a look at this last function that I want to introduce. And this is called a reciprocal function. Again, not a new word. Sorry, can you not see, Ben? You can? Well, please let me, like, I can, is that, yeah? Okay, please advocate for your eyes. All right, reciprocal. We know that the reciprocal of x is 1 over x, right? And as such, here, wait, let me write it differently. Whoa. Um, right, reciprocal of x is 1 over x. So we introduce a function called the reciprocal function. And it is not the opposite of a linear function. Because as you can see from these dots, it actually has two parts to it. So the way that we figure out this function is we start taking some inputs. And so we went into Desmos and plotted some points. So if x is -3, what's the reciprocal of that? Why, it's 1 over -3, right? Notice we're not doing the negative reciprocal like in slope. We're just doing the reciprocal. Okay, so just 1 over. If my input is -2, my output is 1 over -2. Okay, so what does this machine do? Well, it takes your input and it puts it in the denominator. However, it finds the reciprocal because what if your input is a fraction? What if your input is -1 over 3? So what do? Flip, right? Look at my fingers. If you have a fraction, you flip it. So you get -3 over 1, which I don't write the over 1 part. Do you see how I'm getting the outputs? And then I move into the positive. So there's almost like a break here. What if my input is 1 over 3? Well, the reciprocal is 3 over 1. 1/2, I get a 2. What's the reciprocal of 1? Well, 1 over 1, the reciprocal is 1 over 1. So that's interesting, right? The reciprocal of 1 is 1. The reciprocal of -1 is -1. Okay, so do we see how we came up with these tables? Okay. No more questions? Who's got a question? Okay, let's see what happens when we put these dots on a graph. Okay, so when I have -3, the output, the y value is -1/3. Find that dot. Okay, so if x is -3, y is 1/3. Oh, it's here. It's this one. When y is -2, when x is -2, y is -1/2. When x is -1, y is -1. Well, how about when x is -1/2, y is -2? So do you sort of see the pattern in these numbers? Okay. The function is always getting closer to one of the axes. What happens if x is -100? If x is -100, what is y? Yeah, -1 over 100. That's a tiny number. Show me with your finger, how close is that to the y-axis? Like this. What if x is negative a gazillion? What's the y value? 1 over negative a gazillion. How close to the y-axis is that? Okay. So here's my question. When does this function hit y equals 0? Okay? So what is the input that will give you a value of y equals 0? Yeah. Well, let's look at that. Folks, if my input is x equals 0, what is the reciprocal of that? No, 1 over 0. What's that? What's that? That is kind of undefined. And it's undefined because is it a tiny number or a huge number? A ginormous number. It is so big that we cannot define it. We cannot give it a value. So when x is 0, like right here, the value of the function is undefined. The function actually never reaches this line. The function will never hit the y-axis because as we get closer and closer, the y value gets bigger and bigger. Okay? It gets so huge, and then when x is 0, the y value is undefined. So what it means is when the output is undefined, that means there is like a force field that is not allowing the function to get to it. Okay? And that is what we call an asymptote. There is something there. There's like a magnetic force field that's like, no, you're not allowed to get close to me. You're not allowed to touch me. And that is called an asymptote. Okay? And there is, can you guess where the other asymptote is? So I'm telling you that the x-axis is an asymptote. Sorry, the y-axis is an asymptote. Because that function, that line, will never touch the y-axis. Take a wild guess. What is another asymptote for this function? That's right. The x-axis. So I haven't drawn it on purpose. So if I take this graph and I make the x values bigger and bigger in value, the function will get closer and closer and closer to the x-axis, but it will never reach it because that is another asymptote. And in the positive end, the function acts similarly. It gets closer and closer and closer and closer and closer to the x-axis, and it gets closer and closer and closer to the y-axis, but it never actually reaches those axes. It never touches them because we have an asymptote for the y-axis and an asymptote for the x-axis. Okay? And so because the function is never there, it never exists on the on either of those axes, this is how we write the domain. We say, yeah, this function exists on the entire x-axis except where? Yeah. So look, this function is gonna continue going forever and ever and ever to positive infinity and negative infinity. There's one dot where the function doesn't exist. Right there. Where x equals 0, the function doesn't exist. So we're gonna say x belongs to all real numbers with the one restriction that x does not equal 0. Does the function exist at x equals 0.1? Yup. How about x equals 0.000001? Yup. But at x equals 0, there is an asymptote. Can you guess what the range is? Same thing. Why? the function exists on the entire y-axis except at the asymptote where y, so what we're saying is y cannot be 0. Okay, every other part of the y-axis belongs to the function except y equals 0. And so here's the question. Is this function a discrete or a continuous function? It's a continuous function because it is a solid line, but it has asymptotes that breaks them up to almost look like two functions. Does this pass the vertical line test? It does. So it's a function. So let's look at the definition of an asymptote. Okay, so I want you to read this paragraph to yourself. Underline if you need. Yes. Okay, so the asymptote of a curve is the line that the curve approaches but never reaches. And another way of looking at it is that the distance between the function and the asymptote gets smaller and smaller and smaller, but it never gets to 0. So in this parent function, there are two asymptotes. X equals 0 is one of them, and y equals 0 is another asymptote. Why? Because the function will never reach those lines. Because, actually, let's say, because f at x equals 1x, 1 over x, never reaches asymptotes. Asymptotes. Learn the spelling of this new word, asymptote. Yes. Probably 10. All right, let's summarize the reciprocal function in our table. So when I graph the reciprocal function, I really focus on two pieces of information. One are these 2 points, 1, 1, and negative 1. And then I focus on the asymptotes. So I don't focus on those little dots. Now, when I draw an asymptote, I use a dotted line. Okay, so do you see I'm using a dotted line for the two asymptotes? And you must label the asymptotes. I don't want a signature. So I label it as x equals 0 and y equals 0. Okay, so when I'm graphing the parent function of the reciprocal function, I graph the asymptotes, and then I graph just these 2 dots, and then I know, well, the function approaches the asymptote on each end. Approaches asymptote, approaches asymptote. Let's fill in the graph. So for domain, x belongs to the entire set of real numbers such that x does not equal to 0, right? So this domain is a weird one because you're basically stating you're just using the asymptotes. Range, y belongs, we're almost done, to real numbers such that y does not equal 0. Are there asymptotes? Yes. X equals 0, y equals 0. And then for which points to graph? You graph 1, 1, negative 1, and 2 asymptotes. Of x equals 0, y equals 0. Folks, I didn't give you homework for graphing the parent functions, but I would like you to review them and practice graphing them so that when we start transforming them, you know how to graph them. All right, so you have homework on the parent function and you have homework just to review this part.